Okay, Assalamualaikum and good morning, everyone. Okay, so for today's lecture, we are going to learn new topics. So for today, we are going to learn about stability analysis, normal cases, but we are using the method called Routh Hurwitz criterion. Okay, so for this lecture, students will be able to determine system stability using Routh Hurwitz criterion for normal cases. Okay, so alamak, macam ni. Cepat masuk, cepat masuk. Okay. So in automatic control, the most important thing in the analysis is to determine the system stability. So there are, I think the topic after this will involve the stability analysis. So the first topic that we are going to the first method that we are going to learn about stability analysis is by using Routh Hurwitz criterion. Okay, so firstly we define the system stability. Okay, so a system is stable if the natural response approaches zero as time approaches infinity. So if you look at the first figure here, so when this figure here shows a stable system, because if you look at the response or the graph, it reaches zero or a steady state value as the time approaches infinity or as the time increases. And the system is unstable if the natural response approaches infinity as the time approaches infinity. So the second figure here shows an unstable system because the response is increasing as the time approaches infinity. And the third figure here is a marginally stable system, meaning that the system neither grows or neither decay, okay? Neither grows nor decays, but remain constant or oscillate. So if you get a system that is oscillating and for as the time increases to infinity, then the system is marginally stable. So there are three types of stability of a system. You have stable system, unstable, and also marginally stable. So let's look at an example of how to determine a stable system. So let's say if you have a block diagram as shown here. So here the forward transfer function. So the top one here, we call it forward transfer function. And the bottom line here, if you have a box here, so we call this backward transfer function. Okay, if you have a forward transfer function as shown here, then first you need to simplify the block diagram. Okay, so you simplify using feedback formula. So when you simplify, you get I think something about okay, so you simplify like this, and then further expand the denominator here. And then you try to get the root of this denominator. And then we can plot the root in a what we call S-plane here. So an S-plane, basically the y-axis is imaginary axis. J here is square root minus 1 equals j. Or if you learn in maths, we also denote as I, okay? And then you have x-axis, the real part of your imaginary number. So when you find the root for the denominator here, then you plot on the S-plane. Okay, so if you have all the roots on the S-plane on the left-hand side of the S-plane, then the system is stable. Okay, so if we try to find the CT or the time response of C and plot CT against time, then you will see that the graph of CT oscillates and then slowly reaching a steady state value. So this kind of time response is stable time response, okay? Alamak. So stable system have poles only in the left half plane, okay? So kalau poles or the root of the denominator are on the left half plane, then your system is stable. So the root of denominator, so we call this pole, and left hand side meaning stable. Okay, okay, so let's say you have another block diagram here with different transfer function, and then same thing, you find the root of denominator or the poles and plot it on the S-plane, and you will see there are two poles on the right hand side here. Right hand side. Okay, so if you have poles on the right hand side, then the system will be an unstable system. So unstable system have at least one pole in the right half plane. Okay, so if you find the time response and plot the time response against time, then you will see that it will oscillate and then increases even though the time increases to infinity. So it doesn't show any sign of decreasing. So this kind of system is unstable. Sekejap. Oh my. Okay. So if you manage to find the poles and plot the poles on the S-plane, then we can determine the system stability by looking at the poles location only. So stable system has poles on the left hand side, okay? Left hand side. And unstable system has the poles on the right hand side. And marginally stable system has the pole located exactly on the JW axis. Okay. Um, okay, sorry yang tak dapat masuk sebab Google Meet ni dia still tak automatic. Dia kena buka tab dia untuk allow student masuk. Walaupun tapi saya tak payah tekan lah, tak payah tekan admit. It's just that I kena buka window tu. Sekarang ni kan tengah present, so window tu behind the scene, so dia tak boleh nak admit. So every time kena stop presentation untuk allow korang masuk, okay? So siapa yang boleh solve? Nanti kita tahu Okay, so another way of determining the stability of a system is by using Routh Hurwitz criterion. So this method is to know how many poles or closed loop poles are in the left half plane and how many in the right half plane and how many on the imaginary axis. So closed loop system here, meaning that closed loop system poles here, meaning that transfer function yang dah simplify punya block diagram, okay? Meaning that you simplify the block diagram first, and then you get the transfer function, and then from here only you find the poles, okay? So that poles are from the transfer function of the simplified block diagram, okay? Yang dah reduce. So first step is we generate a Routh table, and then secondly we interpret the Routh table. So this method can allow us to know how many poles are on the left half plane, right half plane, and on the imaginary axis. Okay, so let's look at this method, how to generate the Routh table. So let's say you have a transfer function of a system here, something like this. So here it's already simplified. You don't have any feedback loop, okay? So first step that you are required to do is you need to look at the transfer function and look at the denominator. Okay, look at the denominator, and if the denominator starts with s to the power of 4, then your table also must start with s power of 4 and followed by s power of 3, 2, 1, and 0. Okay. After that, you arrange the coefficient alternatingly, okay? So you start with A4 here, followed by A3 down below the A4, and then A2 next, and then A1 below A2, and then A0, and then because here you don't have any more coefficient, then you put 0 on the remaining spaces. So you need to fill the 2 top rows first, okay? Penuhkan 2 row yang pertama alternatingly with coefficients of the denominator. So start with A4, A3, A2, A1, A0, and if you have more spaces or more empty boxes, then you put 0, okay? And then to determine the ada call. Hello. Salam. Okay. Nanti student saya turun. Nanti deal dengan flow itu. Okay, terima kasih. Okay. Dah sampai. Okay, sorry. Ada commercial break. Ya, ada orang masuk tadi. Okay, tak ada. Alright. After that, you need to fill in the next rows, okay? So, for example, row S2, what you are going to do is you need to calculate this determinant. So, this determinant, basically you need to look at row here, A4, A3, A2, A1, find the determinant, put negative, divided by A3 here. And then on the next column, you need to find the determinant of A4, A0, A3, and 0 minus divided by A3. And then for the last column, you find the determinant of A4, 0 here, because you don't have anything here, so you put 0, A3, and 0 divided by A3. So mungkin sekarang ni tak tahu macam mana nak korang nak hafal, tapi bila buat quizzes dan exercise ke, lama-lama korang tahulah macam mana nak determine nombor apa kena letak dalam determinant ni. Okay, but for now just accept dulu. Okay, and then for row S1, the first column, basically you need to use the value of you need to find the determinant for the values of A3, B1, A1, B2 divided by B1. Okay, and same for the second column, A3, B1, 0, 0 divided by B1. Okay, dia macam ada pattern kan, kalau boleh nampak. And then same for S0. Okay, so the method basically requires you to fill in the first two row first with the coefficient of the denominator. So after you fill the two top rows, then the remaining rows you need to calculate the determinant. Okay, so calculate the determinant, you need to follow the patterns. Okay, okay, so just now is how to generate the Routh table. Now how to interpret the Routh table. So the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So after you fill in the table, then you need to look for the first column and determine how many sign changes. Sign changes mean from positive to negative, then from negative to positive. How many times there is a sign changes. So if there are sign changes in the first column, then the system is unstable. Kalau ada sign changes, dia terus unstable. So let's look at an example. Okay, so example here gives you a block diagram, a forward transfer function and a backward transfer function equals 1. So here dia punya transfer function equals 1. Okay, so first you need to simplify the block diagram. So you use feedback formula. Okay, so you get 1000 divided by s plus 2, s plus 3, s plus 5 divided by 1 plus 1000 divided by s plus 2 Okay, rearrange and you will get this. Kalau saya dah selalu buat, kalau dah selalu buat, kita tak payah tulis yang ni pun tak apa. So method dia ialah untuk yang GS ni, untuk dapatkan CS over RS, basically you write 1000, the numerator of GS divided by 1 plus H dia 1, GS dia yang ni. So you want to simplify the 1 plus GS HS. So what you are going to do is you multiply this one by the denominator here, and then the denominator is divided from the numerator of CS over RS. So cara cepat dia just tulis balik je lah, okay? 1000 divided by S plus 2, S plus 3, S plus 5 plus 1000. Mungkin tak faham apa yang saya membebel, tapi bila korang buat exercise nanti, lama-lama korang tahulah, tulis balik je. Okay. Okay, so bila dah dapat yang ni, when you get this trans function, you need to simplify the denominator first. Okay. Okay, simplify the denominator to get a complete equation. Okay. So then you can use the denominator to generate the Routh table. Okay, so since here it's S power of 3, so you start your table with S power of 3, S power of 2, S power of 1, S power of 0. And then you fill in the two top rows. So you fill the first two top row, S3 and S2. Okay, 1, 10, 31, 1030. Okay. And then here you have empty column here, so you just put 0. And then to determine S1, basically you need to determine the determinant from the row above. So negative 1, 1, 31, 100, 1030 divided by 1. Okay, divide by this one. Okay, so here dia kira dapat minus 72. And then to determine the next column here, so you use the value determinant of 1, 10, and this 20 here divided by this. So you will get 0. And then repeat for row S0. Okay, so in Routh table, you can factorize a column, okay, a row here. For example, this row here, the second row, this one you should fill in with number 10, and this one is 1030. So because you can factorize each row, then you can factorize 10 here. So dia simplify jadi 1 dan 103, 1 and 103. If you don't factorize pun okay, doesn't matter. So here you factorize, maybe you can calculate the next row easily. But if you don't factorize, also okay, tak salah pun. Okay, after that, you need to look for sign changes in the first column. Okay. So in the first column, from S3 to S2, it's +1 and +1. So no sign changes here. And then from S2 to S1, you have +1 and -72. So you have one sign changes, one sign change here from positive to negative. And then from S1 to S0, you have -72 to +103. So you have another sign change. So from the first column, you have two sign changes, meaning that you have two poles on the right hand side of the plane. So the system is unstable. So kalau ada dua sign changes, meaning that you have two poles on the right hand side. If you have one sign change, then one pole on the right hand side. Okay. So kalau ada sign changes je, terus unstable system tu. So the usefulness of Routh Hurwitz criterion is that if you look at our if you look at our first slide just now, untuk determine the stability, we need to determine the poles and plot the poles on the S-plane. So sometimes the transfer function can be very long, okay? And it's very hard for you to factorize the denominator, especially to determine the poles. So the purpose of Routh Hurwitz criterion basically to allows you to determine the system stability without factorizing the denominator, okay? Without finding the poles. So method ni tak payahlah nak kena factorize equation ni guna calculator ke, mungkin susah, okay? So guna Routh Hurwitz table dah boleh dapat dah system stability. Okay, so usually in exam the kind of question related to Routh Hurwitz is to determine the range of K, of a gain K for the system to be stable. Okay, so let's say you are given a transfer function, a closed loop transfer function as shown here. So first step you need to do is to arrange the denominator to generate the Routh table. So 1, 18, 77, and K. Okay, just fill in with the coefficient. And then determine the subsequent row. So here S1 is determined by denominator, determinant of -1, 18, 77, and K divided by 18. And then here it's 0 because it's determinant of 1, 18, 0, 0 divided by 18. So you get 0. And then for the next row, you get K. And then here also 0, okay? So how to determine the range of K for stability, for stable system? So first you need to look for the first column, okay? So for stable system, the first column must have no sign changes, meaning that no negative values. So here it's already positive. The first row S3, row S2 also positive. And here our row S1 has a variable K here. So to determine the range of K, so you make sure that the term here must be always positive. So from here you can determine K. So K is must be less than 1386 for stable system, or for this row to be positive. And then the row S naught, you have K here. So for stability, K must be positive. So K must be always bigger than 0. Then you combine the two range here. So the range of K for stable system is from 0 until 1386. Habis dah slide. Okay, so that's it for today's lecture. Siapa nak masuk tadi? Okay, any question before we end our lecture? So the basic concept here, you need to understand how to generate the route table and then determine how many sign changes in the first column to determine how many poles on the right half plane or right hand side of the plane. Then if you have sign changes, then the system is unstable. And then some question might ask you to determine the gain K. Okay, to determine the gain K, first you need to generate the route table and find the sign changes in the first column, and make sure that the sign change the first column must have no sign changes. Okay, meaning that all must be positive. All rows in the first column must be positive. Then you can determine the range of K. Okay, so bolehlah try quiz number 8. And next week, we are going to learn Routh Hurwitz criteria juga, but for special cases. Okay, so here it's normal cases, and next week we are going to learn on special cases. And this topic also will be used in lecture 4, I think, in chapter 4, because chapter 4 you will use Routh Hurwitz table, but how to say, the usage is quite a lot. So I want you to practice from now on understanding to understand the Routh Hurwitz criteria, how to generate the table, because in chapter 4 you are going to use it many times. Okay, a lot of times. Okay, so if you have no question, then see you next week, inshallah. Assalamualaikum and goodbye.
Thank you, sir.
Thank you.
Yes, sir.
Thank you, sir.
Thank you. Besar ke lori dia? Banyak ke barang tu? Oh, kita orang first lah. Nah?